welcome back. We will continue with computing some more integral and find out some large class of functions which are Riemann integrable. So, in the last lecture we have computed x integral over x from a to b, we have computed integral over x square from a to b. So, similarly we can more examples, we can compute a to b of x cube dx. So, I will leave much of it as an exercise. So, you take a partition P, take P and you define S P of f. Here your f of x is equal to x cube. Now, to be summation over k from 1 to n f of c k x k minus of x k minus of 1. Now, you choose your c k to be x k cube plus x k square x k minus of 1 plus x k minus of 1 square plus x k minus of 1 cube divided by 4 whole to the power 1 over 3. Now, as you can see that easily that x k minus of 1 q is lesser equal to c k cube. So, which is again lesser equal to x k cube. So, therefore, c k is lying between x k minus 1 to x k, and if you put this value of this c k, then this is going to be summation over 1 by 4 is going to come out, because cube if you take f of c k is c k cube. So, 1 by 4 is going to come out k equal to 1 to n of this x k cube plus whole into x k minus of x k minus of 1. This easily you can see that this is summation over k from 1 to n x k to the power 4 minus of x k minus 1 to the power 4, and so this is 1 by 4 of b 4 minus of a 4. So, that is what is going to be the integral of a to b x cube dx. Okay. So, now another interesting example let us find out is that integral, let us say 1 to 2 of dx by x square. We do not know why. So, rather the question is take f of x is equal to 1 by x square when 1 is lesser equal to x lesser equal to 2. So, is f Riemann integrable on 1 2 interval? If so, find so this is the proper question. Now, in order to do that, what we need to consider a partition P, any partition P. Now, S P f is equal to summation over k from 1 to n f of c k, that is square, this is 1 by c k square of x k minus of x k minus of 1, where c k is between x k minus 1 to x k. Now, our job is to choose our c k cleverly, so that we can sum it up. Now, choose c k, let, and this is where the freedom of Riemann is coming, that we can actually we have the freedom to choose any c k what we like. So, if we choose square root of x k, so now we will choose our c k. So, let us take c k to be square root of x k minus 1. This is the partition of 1 and 2. So, all these are positive numbers. So, we do not have any problem in taking the square root. Now, as you can see that x k minus of 1 square is less or equal to c k square, which is less or equal to x k square. So, c k is lying between x k minus 1 to x k. So, that is a very good choice for us. Now, this is going to be k from 1 to n 1 by x k minus of 1. These are all non-zero quantity. So, we can divide them, and x k minus of x k minus of 1. This is going to be summation over k from 1 to n 1 by x k minus of 1 minus 1 by x k. Now, this is again a telescopic sum. So, what we are going to get is that 1 by a minus of 1 by b. So, that is why for each partition P, by choosing C k cleverly, we found that S p of f, the Riemann sum for this partition, is going to be 1 by a minus 1 by b. So, limit norm p goes to 0, S p f is going to be 1 by a minus 1 by b. Therefore, we say that if not only f is Riemann integrable on 1 2 and the integral over 1 to 2 dx by x square, this is equal to 1 by a. So, this is a is 1 here, b is 2 here. So, this is 1 half. So, this we can write it as half. Okay. So, at least we are able to compute some integrals by using Riemann sum and Riemann's prescription basically. Now, let us look at some large class of function, which by looking at them we will say that okay, definitely they are going to be Riemann integrable. So, let f from a b to r be monotonic. That means either it is monotonically increasing or it is monotonically decreasing. Then f is Riemann integrable. What we have seen? We have also seen that in order to show that f is Riemann integrable, if given any epsilon positive, if we can find a partition P such that U p f minus of L p f is less than epsilon, then we definitely can say that f is Riemann integrable. So, now for this monotonically increasing, assume f monotonically increasing. So, consider the partition P such that x k minus of x k minus of 1 is equal to b minus of a by n. For some n you consider this partition. Then you know U p f, this is going to be what? This is between, so this is summation over k from 1 to n, this is m k x k minus of x k minus of 1. What is mk? Mk is going to take the value on maximum between xk minus 1 and xk. So, this is nothing but summation over k from 1 to n f of xk into xk minus of xk minus of 1, because this is an increasing function. So, here it is xk minus of 1, here it is xk. So, here at xk minus of 1, this is f is going to take the maximum value. So, now LPF, this is equal to similarly summation over k from 1 to n, little mk which is the minimum value, because we are assuming this to be an increasing function. So, this is k minus of 1 x k minus of x k minus of 1. Therefore, UPF for this particular UPF minus of LP of f, this is equal to summation over k is equal to 1 to n f of x k minus of f of x k minus of 1 into x k minus of x k minus of 1. Now, we are choosing a particular partition which is the x k all equal length. So, this is going to be b minus of a by n summation over k from 1 to n f of x k minus of f of x k minus of 1. This is again a telescopic sum. So, which is going to survive only at the end point. So, this is f of b minus of f of a. Now, this is a finite number, this is a finite number. So, now n divided by n, what we want is that we just want to get a partition P such that UPF minus of LPF will be less than epsilon. So, now for every n, this is what we are going to getting for this particular partition P. Therefore, and in the numerator there is a finite quantity. So, what we can take is that take n large, take n large such that b minus of a into f b minus of f a divided by n is less than epsilon, and then UPF minus of LPF it is going to be less than epsilon. That shows that if f is monotonically increasing function, then f is Riemann integrable. So, that is very nice to see, and the next is that let f from a b to R be continuous. Then f is Riemann integrable. This is a pretty decent result that any continuous function is Riemann integrable. I am not going to give the proof for this because it involved a little technicality of the behavior of the continuous function on closed and bounded interval. So, maybe in an advanced calculus course, you will appreciate it more than here. So, this we will assume, I mean we will take it for granted, you have to grant me that if f is continuous, then f is Riemann integrable. At the very beginning of the Riemann integrability, we have seen that even there is a discontinuous function, that is also Riemann integrable. So, it is not necessarily that only the if it is Riemann integrable, then it is going to be continuous. So, now let us recall very quickly what is Riemann integrability. Now, what we are trying to do is that we are trying to get the Riemann sum, and Riemann had told us that with a partition P you can choose cleverly your C k, any point C k between x k minus 1 to x k will do, as long as if the Riemann sum goes to a limit when you are taking your partition to be inside the partition, the length to be very small. That means, norm p goes to 0, then and every continuous functions are Riemann integrable. Functions which are discontinuous may be Riemann integrable. Then the important question is that have we really seen a function which is not Riemann integrable? Is every bounded function Riemann integrable? The answer is no. So, define, let f of x, this is equal to 1 if x belongs to q intersection of 0 1 and 0 if otherwise. And I am defining a function f, this function is only on 0 1 to r. Okay. Now, look at u p of f. U p of f, you take any partition p, which is equal to x naught x n. Now, you consider x k minus of 1 to x k. In this interval, definitely there are going to be rationals, in any interval is going to contain rationals. So, therefore, the maximum in this interval is going to be 1. So, this is going to be summation over k from 1 to n x k minus of x k minus of 1, which is nothing but equal to 1, because again a telescopic sum which is equal to x 0 is equal to 0 and x n is equal to 1. Therefore, what you are going to get that U p f is 1 irrespective of whatever partition you take. Now, let us get L p of f. This L p of f is going to be minimum of f in the interval x k minus of 1 to x k. Now, this interval x k minus of 1 to x k will definitely contain irrational, and f is going to take the value 0 in those irrational points. Therefore, the minimum is going to be 0. So, this is 0 into x k minus of x k minus of 1, which is equal to 0. So, therefore, for every partition P, partition P U p f minus of L p f is equal to 1. So, it can never be small. In other words, you can choose your take a partition P, then if you choose your S p of f, then if you choose your C k to be irrational, you are going to get 0. If you choose your C k to be rational, somebody else will choose C k to be rational, then what you are going to get to be 1. So, this shows that it can never, this difference can never be small. So, f is not Riemann integrable. But obviously, f is a bounded function, but f of x is always lesser or equal to 1 and greater or equal to 0. F is a bounded function, but it may not be Riemann integrable. It kind of saying that I mean too much of oscillation, rapid oscillation is not a good thing to happen for the case of Riemann integrability. Then world has to wait for a long period of time how to get rid of this problem, but that is beyond the course. Okay, so now once we have done with what is defined to be Riemann integrable or not, so let us look at the algebra of the Riemann integrable function. So, what one says that if f and g both are Riemann integrable, will f plus g alpha times f g, all these things are Riemann integrable or not. So, theorem, let f g their function with a b to r both be Riemann integrable function. Okay, so then 1, if I take a to a f of x dx, then this is going to be 0, because there is no partition which is happening this single term, this is 0. If I take a to b f of x dx, then this will be equal to minus b to a f of x dx, because so integral a to b some alpha f of x dx, this is equal to alpha times a to b f of x dx for any alpha belongs to real line. Integral a to b f plus g of x dx, this is equal to integral a to b of f of x dx plus integral a to b g of x dx. So, let a is less than c is less than b, then integral a to b f is equal to integral a to c f f x dx plus integral c to b f x dx. And then minimum of f is a bounded function. So, which has minimum and the maximum what we are going to take, and this times b minus of a is lesser equal to integral a to b f of x dx, which is lesser equal to maximum of f into b minus of a. And also if f of x is lesser equal to g of x, then integral a to b f of x dx is a to b g of x dx. So, integration Riemann integration also respects the inequality order. Okay, so the proof I will just sketch, which is not very hard. I mean, you can do it on yourself. Suppose I will use this portion, so that it will be clear. Now, let us try to see that, I mean, how to prove this 3. So, this is for 3. What you are looking at, take a partition P. So, you are looking at alpha for the function of alpha f. So, this is equal to summation over k from 1 to n alpha f of c k and x k minus of x k minus of 1, which is equal to alpha times summation over k from 1 to n f of c k and x k minus of x k minus of 1. Now, we are given that f is Riemann integrable. So, this quantity, this is nothing but this is alpha time s p of f. Now, we know that limit SPF norm P goes to 0 exists. So, limit norm P goes to 0 S P of alpha f exists, and that is equal to be alpha times limit norm P goes to 0 S P of f, which is equal to alpha times integral a to b of f of x dx. That is what we know. So, similarly, for f plus g, you consider a partition S P of f plus g. This is equal to summation over k from 1 to n f plus g of c k x k minus of x k minus of 1, which is equal to, because these are all finite sum. So, what you can do is that can separate this is g x k minus of x k minus of 1. This is essentially S of P of f plus S of P of g. Okay. You see, this P is also, your partition P is dependent on the choice of C k what you were taking. So, now as you can know that you take norm of P goes to 0, this side exists, right hand side. So, left hand side is going to exist, and so this is going to be the integral of f plus g, this is integral of f plus integral of g. Thank you.